Visualizing Lyft's self-driving car data, the open source way. Our goal is to visualize Lyft's Level 5 open data on their self-driving cars in an open source way for the first time ever. While there are pre-existing methods to visualize this data using Python and Jupyter, they restrict visualization to only one frame at a time. Our approach will make it available in open standard and more accessible. The technologies we use for this project are Cesium Ion, CSS, JavaScript, Glitch, Cesium.js, Python, and HTML. The team is comprised of Ian Liu, Shania Dhani, and Mehrab Hafiz. My goal for this project was to convert the perception data from raw bin files Lyft publicized to LAS files, which are compatible with Cesium Ion, and upload these LAS files onto Cesium through the REST API. Perception data is one of two types of data published by Lyft, the other being prediction data, which Mehrab has been working with and will talk about later on. Perception data is the raw data picked up by the self-driving car's laser. I was also tasked with applying point cloud shading to the final animation. The process began with converting the raw data. It was difficult to determine the format of the data at first, but it was discovered to be in the new scenes dataset format with data type float32. The source code in the linked dev kit and the Yumpy and LASP libraries converted the bin files directly into LAS files. The maximum and minimum constraints for each component, those being X, Y, Z, and intensity, were also calculated using lists, and here we can see an example of the output. A possible improvement to be made is to change the scale component of the LAS file upon conversion. This will render the files smaller, which, as we will see later on, would be beneficial as the data points were larger than the area it was mapped to. The next step was uploading the data. I followed the linked REST API first and was able to upload small batches of files, 100 at most. However, when attempting to upload a larger batch of 1,000 files, numerous 504 gateway errors were received. This was due to the files being processed in parallel. To amend this, the files were uploaded sequentially by using a for loop instead of a for each with async await on the upload file function. Due to the first test run uploading improperly, a script for listing all asset IDs and deleting them was written with help from the linked API guide. We can see the script in the lower right-hand corner. Another problem we ran into was that the initial files were uploaded without a position option. This was because the files weren't georeferenced. Georeferencing is where a file is in the physical world, and we didn't know where this data was collected geographically. This was an inconvenience as we had to set the tileset position for each file. To remedy this, the position of each file was set to 000 as seen on the left. This is the point cloud shading of the final animation. Our goal was to visualize the point cloud data in a manner that would be easier to digest, as exemplified by the sandcastle in the upper left. This was achieved by adding eye dome lighting and attenuation in the toolbar, as we can see in this video. This being the attenuation, and this being the eye dome lighting changing. An improvement we can make in the future is to have the toolbar adjustments apply permanently to the rest of the animation instead of statically to one frame as it is right now.
My goal for this project was to visualize the converted LiDAR data using Cesium.js. To achieve this, I had to first figure out how to position and animate the data set in a Cesium scene. Next, I had to map a 3D car model on top of that data and color the data in a way that was meaningful to the visualization. One major problem we encountered in visualizing the data was that the perception point cloud frames did not have a geographical location attached to them. Because of this, when we uploaded these frames into Cesium Ion recomputed an origin for each point cloud frame. When we translated those frames to a single coordinate in Palo Alto, this resulted in the jagged movement of the point cloud frame shown in the picture here. Ideally, these frames should be resting on top of each other, but since the origin was reassigned, we were unable to visualize the data in a contiguous manner. Thus, to fix this issue, we had to upload our point cloud frames with a fixed position at the surface of the Earth. Since it is not easy to move the frames after they are positioned in Cesium from the surface of the Earth, the following function was needed. Here we move each frame from their fixed position on the surface of the Earth back down to the center of the Earth and translate its position from there back to Palo Alto. Because they weren't georeferenced, Using the positioning logic, we were able to add our point cloud data frames into our cesium scene using this loop. Since we uploaded our point cloud data frames into cesium ion as assets, we referenced their respective asset ID numbers in this loop to add them to our cesium scene. Each frame's longitudinal position is shifted by 500 thousandths to visually emphasize the distance between each frame in reality and simulate motion. This gives us a guess of where the car is moving. This snippet of code ensures that only 2 point cloud frames are shown every second. In reality, given the vehicle speed, it's likely that these frames would be moving much faster. By connecting each frame to a point in time, we get the impression of motion between the frames. Since the only information included in the perception dataset were the point cloud locations themselves, these locations were significant in coloring the point cloud data in a meaningful way. Color is assigned in the point cloud by computing the distance from every single point to the center of the dataset. Each point cloud frame contains 30,000 points. By using the code above, we run this calculation efficiently on the GPU. This results in this heat map coloring. This code snippet positions this 3D car model to the center of the current point cloud frame. Since these frames are not georeferenced, and is thus relying on the path formed by our constructed point cloud frames, we see that our car model is running over houses. That being said, one way we can fix this in the future is by constructing a separate path for the car and point cloud data to move along, and importing that path into this scene.
For the project, I focused on the prediction dataset. My primary goal was to extract driving data from the dataset so that I could visualize how a driving scene plays out on cesium. And then my secondary goal was to show what the car predicts at a given time frame. The challenges for this project was converting the location into real-world coordinates, which is important if we want the car to be at the correct position in the world. And another challenge was visualizing an entire scene on cesium, which includes not only just the car, but all the other traffic agents that are near the car. The data set comes in the Z array format, which is essentially 3 arrays. The scene array has multiple driving scenes, essentially 25 seconds of the car driving around the city, and each scene has multiple frames. A frame is a snapshot of a car at a given time frame, and a frame also shows all the other traffic agents that are near the car. This is the whole data structure for the prediction data set. It's just these three arrays. It's flat, which means that it gets all combined into one big array, and then if we want to go from scene to frame, we could use the index to jump to the frames that we want for a given scene. And does the same thing for to get all the agents that are in the frame. We could use the index and then locate the frames that live on the same array. This is important because we're working with a large data set, and we want to access the data fast. A scene has 250 frames. The samples were collected at 10 hertz, which means there are 10 frames per second. A frame could have multiple agents, and it could also have no agents. The label probabilities for an agent tells us the type of agent that it is. It could be a bicycle, it could be a car, it could be a tree. We use the L5 kit to parse this data. It's mainly built for training machine learning modules, but it also has a nice way to visualize the driving scenes. It's a Python library, This is the demo. For example, in this scene, the car is driving straight, and we could see the pink line represents the prediction where the car is most likely going. Here's another scene that shows the car parking, and the prediction line disappears because the car won't be moving anymore. Uh, the challenge is again we're putting the car at the correct position in the world. I tried to convert these since it comes with instead of giving us the exact location, it only gives us the translation points. It was difficult to directly put it in cesium. I tried to translate these points into latitude and longitude with the built-in matrix that comes with the L5 kit. But in the end, it only gave us the translation into latitude and longitude and not the exact points that we need. The next thing we tried was setting up an origin point and then maybe move the car from there. But I searched the forums. We couldn't find an origin for this system. Um, the last thing we did was syncing of the prediction frames with the LiDAR data. If we if the LiDAR data is already in the correct position, we could just put the car in the center and the car would be in the correct position as well.
Next steps. Some improvements that we could make to our application include tying the data to the correct geographical position in Palo Alto, so our car model isn't running over houses. This may be provided in Lyft's dataset, but it would take some more analyzation in order to find it and utilize it. We would also like to include the prediction dataset to better visualize and identify point cloud clusters as other vehicles, buildings, and pedestrians. We would like to extend a special thanks to our mentor on this project, Omar Shahada, and Code for this opportunity. For those of you who are interested, we have included some additional resources. Here's a link to Lyft's Level 5 open data that we used in our project. In this link, you will see both the prediction dataset and the perception dataset. And here's a link to our live project. Thanks for watching!